Hi everybody, this is Dr. Bricker here with a short video on the last half of Chapter 5, the application of Newton's laws. So we'll be talking about section 5.5, which is friction, through 5.7. Okay, and this last part of the chapter covers homework number 4. Okay, so we're going to see we have two different kinds of friction. We've already talked about it in class. We'll just talk about it in more detail here. So static friction is the force that a surface exerts on an object before it starts moving. So in the picture here you can see that this is not moving yet. The person pushes, it doesn't move. The person pushes harder, it does not move. So if the person's pushing harder and it doesn't move, the frictional force must increase. The harder and harder you push, the bigger and bigger the frictional force becomes, until finally you break it loose. And then when you break it loose, it starts moving, you have kinetic friction. So static friction is the frictional force before it moves. And in a way, it's kind of a smart force, the way I think about it. It's only as large as it needs to be. So if the person pushes with 10 newtons, maybe static friction is only 10 newtons. A person pushes with 20, static friction is 20. All the way up until you get to the maximum amount of static friction. And then once you've overcome the maximum amount of static friction, then again you have kinetic friction. Let's take a look at this PHYS. So you've seen this before. We did the lab on this, Newton's second law. So I'm going to go back to acceleration. And if you notice, I can push a little. 50 newtons, it's not moving. Here's the sum of the forces, values, acceleration. So this is kind of an incomplete free body diagram. Applied force, frictional force. There's also the normal force pointing up, the weight pointing down. But just horizontally speaking, I could increase this, 51, 52. Actually, I think I've got to go up quite a lot more than that. So right now I'm applying 102 newtons. I only have 102. It's not enough to overcome friction. So I'm still in the static friction area. Okay, as you see, I'm increasing this 120, 121, 23, 24, 25, and then I overcome friction. I'm going to pause this. So anything over 125 newtons will get this thing to actually move, and now I have kinetic friction. So the maximum amount of static friction that I had was 125 newtons. And we'll see that the amount of friction you have is also related to the amount of mass that you're trying to move. It's related to the mass because the normal force is involved. Really, it's related to the normal force. So if I put more mass on here and I try to get this to move, it's not going to move. Let me actually reset it and try to get this to move. I'm applying 100 newtons, 150 newtons, 200 newtons, 250. So same thing. Here's the values, acceleration. So I have not overcome the maximum amount of static friction here either. So static friction is related to the normal force and also the materials here. So you could have something that's not as sticky, for lack of a better word. Put this on ice, you would see that the amount of friction is less. And here I'm changing the coefficient of static friction. Now the coefficient of static friction is, it's just a number, there's no units. It tells you the amount of, the maximum amount of static friction you could possibly have. So rubber on concrete has a different coefficient of static friction than, say, wood on ice. It would have a different value. Okay, let's go back to the PowerPoint. Okay, very good. So the box is in static equilibrium. Remember, that means it's not accelerating. In this case, it's not even moving. So the frictional force must be exactly balancing the pushing force. And then once you get the pushing force over the maximum amount of static friction, that's where it actually starts to move. So the harder the woman pushes, the harder the frictional force. And you can see here, it's only as big as it needs to be. Only as big as it needs to be, but larger because the person's pushing harder. And then you get to the point where it's a maximum, just like the crate example we saw. And then once you exceed the maximum amount, then you have kinetic friction. So the maximum amount of static friction from the formula that you see here is equal to the normal force times mu sub s. So this is pronounced mu sub s, the coefficient of static friction. That's just determined by the two surfaces. As I said, rubber on concrete has a different coefficient of static friction than, say, wood on wood. Okay? So that's the maximum amount of static friction. Just in general, the amount of static friction that you have is less than or equal to mu sub s times the normal force. Okay? The useful way of looking at the formula is where it's equal to, you can figure out the maximum amount, but just to be specific, the amount you have is less than or equal to mu sub s times the normal force. Okay, so static friction is the opposite the direction something's moving. It adjusts itself from to how big it needs to be to keep something from moving. Okay, and to figure out the maximum amount, that's where it's actually equal to the normal force times mu sub s. Kinetic friction, on the other hand, is maybe a little bit simpler. It's just equal to the coefficient of kinetic friction, so that's a different value, times the normal force. And the coefficient of kinetic friction is less than the coefficient of static friction. So kinetic friction is always less than static friction. And here you see the formula for it. Okay, we'll have a little table of values of mu sub s and mu sub k. Okay, so this box is being pushed slowly. Here's the speed. This is a static situation where it's actually already started moving. You might say, why are these equal to each other? Well, you got it moving, and now you're just keeping it moving at a constant speed. Okay, and this mu sub k, no matter how fast you're going, see here you're going faster, here you're going slower, this coefficient of kinetic friction and this value of kinetic friction is just going to be whatever it is, mu sub k times the normal force. Here are some values. We're not going to be talking about rolling friction in this class, but rubber on concrete, it's 1, coefficient of static friction here. For kinetic friction, 0.8, so it's always lower. Kinetic friction is always lower. So this goes to the idea, if you try to push something, it's hard to get it moving, but once you get it moving, you can generally keep it moving. That's because kinetic friction is less than static friction. Okay, a little bit of a summary of what we've just said. And again, we're not going to be talking about rolling friction. Okay, so again, this is a nice summary of what I've said. Hopefully you find it useful. So let's take a look at this one. A box with weight 100 newtons is at rest. It's pulled by a 30 Newton horizontal force. Does the box move? Well, what we have to do is figure out the maximum amount of static friction. Okay, so we definitely need a free body diagram for this. I'm just going to actually put it on the picture here. So here's the normal force. Here's the weight, which is equal to m times g. And then we've got friction this way. We don't know right now whether it's static or kinetic. What we can do is figure out if this is even going to move. So let's figure out the maximum amount of static friction. So maximum normal times mu sub s. Now in this picture, the normal force is up, the weight is down. Those are the only vertical forces. The normal force is equal to mg. mg times mu sub s. So what we're trying to figure out is the maximum static friction less than 30. Or is it greater than 30? That'll tell us if it moves or not. If the maximum amount of static friction is greater than 30, it's not going to move. So let's put some numbers in here. Okay. So the weight is 100 newtons. mg is 100 newtons, they're telling us. So 100 newtons, that is mg. And then mu sub s is 0.4. So the maximum amount of static friction is 40 newtons. So if you only apply 30 newtons, this is not going to move. So does it move? No. How much is friction in this example? Well, because our applied force here, the 30 newtons, is less than the maximum amount, the amount of static friction we have is 30 newtons, right? It's only as large as it needs to be. If the applied force here was 31 newtons, static friction would be 31 newtons. If the applied force was 35, static friction would be 35. It's only as large as it needs to be. Now, if the applied force was, say, 50 newtons, it's bigger than the maximum amount of 40, then we would have kinetic friction. Notice I used mu sub s here, not mu sub k. We look for the maximum amount of static friction. All right, excellent. So here's an example we can take a look at. And it says down here, do 527 and 528. We'll do that in class this week. Carol wants to move her 32 kilogram sofa to a different room in the house. She places sofa sliders, which are slippery, under the carpet, on the carpet under the feet of the sofa. She then pushes the sofa with a steady speed of 0.4. Okay, steady speed. It doesn't really matter what the speed is, steady speed. That means it's not accelerating. How much force does she apply to the sofa? So we are looking at what's going on a moment in time. She's already got it moving. Probably it was accelerating in the beginning right after she broke it loose, but now she's just pushing it with a constant speed. So this force that she has this way has to be equal to the force back the other way. So her applied force has to be equal to kinetic friction. That gives us no net force. Forces are balanced. So really we're trying to figure out how much force must she apply. Well, she must apply this much, because then it'll be equal to her force that way. Okay, so if we can figure out the amount of kinetic friction, we can figure out what her force has to be for this snapshot in time. Okay, so remember what we have here. The amount of kinetic friction, normal force times mu sub k. Now in the picture you can see that the normal force has to be equal to mg. And then I also, don't forget the mu sub k part. Whoops. Got a little close to the edge there, mu sub k. Okay, the mass, that's 32 kilograms. I don't have room to put the units here. Times 9.8, and then times 0.08. Okay, completely ran out of room. I'm going to write it over here at the bottom. So we've got 32 kilograms, 9.8 meters per second squared. So kilogram meter per second squared, that's a Newton, and then times 0.08. And there's no units on that. So put that in your calculator, see what you get. Should be something around, let's just get an idea. 32 times about 10 would give us 320 times 0.08, which is about 0.1. So something around maybe around 30 or so. Okay, but you put the numbers in, you come up with it. And again, note, it doesn't matter that it's 0.4 meters per second. Steady speed, the point that you get from that is that it's not accelerating. Okay, excellent. So causes of friction. So all surfaces are very rough on the microscopic scale. This is a nice picture of thinking about that. They're kind of jagged edges, as you can see here in this picture. So when something's at rest, the parts are sort of compressed together. Once you can break it loose, you can think about one surface kind of riding over the other surface. So static friction is before you kind of break it loose, and then once it's broken loose, then you have kinetic friction. Okay, here's another quick check we can take a look at. A box is being pulled to the right over a rough surface. So the tension is bigger than kinetic friction. So the box is speeding up. Suddenly, the rope breaks. What happens? So you're pulling it along just fine. The rope breaks. What's going to happen? Let's look at the free body diagram of this. So this is the free body diagram after it breaks. Normal force, weight, those are equal to each other. So after it breaks, we still have kinetic friction. Now, is there any force to the right? There's not. There's no actual other force to the right. This is after it breaks. Before it broke, there would be a force to the right. After it breaks, we've got kinetic friction. We're not pulling it to the right anymore. It has some momentum, so it continues to the right, but it's going to slow down and stop, right? Because there is a net force back this way because of the kinetic frictional force. It doesn't stop immediately. It goes for a while, and then it's going to stop. So let's read through these. Stops immediately. No, it doesn't stop immediately. Continues with the speed it had before the rope broke. Well, for a split second, and then it slows down. Continues speeding up for a short while. No, as soon as the rope breaks, it's not speeding up anymore. Keeps its speed for a short while, then slows down. guess it depends on what you mean by a short while. It doesn't do that. It immediately starts slowing down. So it's not this. Slows steadily until it stops. So it's got to be E, right, based on that free body diagram. Okay, excellent. A little bit about drag force. Unless the problem specifically tells you that there's a drag force, we'll not look at drag forces. But it's kind of fun to talk about what it is, actually. Opposite in direction to the velocity. So if something's moving one way, drag force is back the other. If you're riding your bicycle through the wind, the faster and faster you go, the bigger and bigger the drag force is. As it says here, increases in magnitude as the object speeds up. At relatively low speeds, the drag force in air is small and it can usually be ignored. So unless we tell you otherwise, ignore it. But some problems we can actually solve for it. Okay, so fortunately we can use a fairly simple model of drag if we can meet three conditions. The object size is relatively small, between a few millimeters and a few meters, speeds less than a few hundred meters per second, and moving through air near the Earth's surface. Those are the three conditions that we'll have here. And here's the formula for those conditions. 1/2 C sub d, density times cross-sectional area times speed. So rho, that's how this is pronounced, it's the density in air. So at sea level, it's about that value, 1.2 kilograms per cubic meter. Now the cross-sectional area is, if you're going, say you're riding your bike, the cross-sectional area is your area that's going through the wind. So if you want to kind of reduce drag force, you can scrunch yourself down and you make your effective cross-sectional area smaller, the area that's actually going through the wind. Okay, the drag coefficient, that's C sub d here, depends on the details of the object's shape. So for everyday objects, it's about 1/2. So if you take this 1/2 for C sub d, plug it in here, you get this formula finally. Okay, so drag force 1/4, density of air, which we actually know, 1.2. Cross-sectional area is whatever that turns out to be, and then V is the speed that you're going. So you can see the faster you go, because it's proportional to V squared. This is the way to write that. The faster you go, the bigger the drag force is. So if you go twice as fast, the drag force is actually 4 times as much. Now, terminal speed is when the weight, the force of gravity pulling you down, is equal to the drag force. So if you drop something off, say used to be called the Sears Tower, it's going to speed up, speed up, speed up. The faster it goes, the bigger the drag force becomes, until the drag force is equal to the weight, and that's where the thing will actually stop. Stop accelerating, I should say. It keeps moving with something called terminal speed. So terminal speed corresponds to the point where the drag force, pointing up, is equal to the weight that points down. This is for something that's falling. Okay, we can take a look at this example. A skydiver and his pet mouse jump from a plane. Estimate their terminal speeds, assuming that both fall in the prone position. Okay, with limbs extended. So there's no net force once you reach terminal velocity. You were speeding up and speeding up and speeding up. Drag force became bigger and bigger and bigger until you get to the point where those are actually equal to each other. And we can solve for these different drag forces, terminal velocities. So estimate their terminal speeds, assuming they both fall in the prone position. So now the man there has a certain cross-sectional area and mass. The mouse here has a certain cross-sectional area and mass. So let's look at the formula for what terminal speed is. Okay, so now what you see there is the free body diagram over here. And we're at the point where the drag force is equal to mg, and the drag force is 1/4 density of air, cross-sectional area, times the terminal velocity squared. I'm calling it terminal velocity because that's, again, the point where the drag force is equal to mg. So that's equal to the weight, which is mg. A little bit of algebra to solve for the terminal velocity. So multiply both sides by 4, divide by the density and the cross-sectional area, take the square root, and you finally get this for the terminal velocity. So it depends on really the square root of the mass to area ratio. Now, if you look at the mass to area ratio of the man, it's a lot bigger than the mass to cross-sectional area ratio of the mouse. So the terminal velocity of the man is a lot bigger than the terminal velocity of the mouse, just owing to the fact that the mouse has a small mass and a relatively larger cross-sectional area, relatively speaking, than what the man has. So to figure out the terminal velocity, 4 is just a number. You can put in the mass of each. You have to do this for the mouse and then do this for the man. G is just 9.8. The density, again, that's the density of air, and then A is the cross-sectional area. So for the man, you can figure out the cross-sectional area. For the mouse, you can figure out the cross-sectional area. Put everything together, you'll see that the terminal velocity of the man is a lot bigger. So the man accelerates to a greater speed before not accelerating anymore than the mouse does. Okay. So assess. The terminal speed that you calculated for the skydiver is close to what you'd expect if you looked it up. What about the mouse? The terminal speed, again, depends on the ratio of mass to area. So smaller values lead to slower terminal speeds. Small animals have smaller values of this ratio and really do experience lower terminal speeds. A mouse with its very small mass to area ratio and therefore small terminal speed can typically survive a fall from any height with no ill effects. Small animals can reduce their terminal speed by increasing their area. You hold your arms out to the side, things like that. Now, if you look at the picture in the start of the chapter, there's a frog in the picture with its all stretched out. They're doing that to increase their area and therefore reduce terminal speed. Okay. So here's a catalog of forces again. We've looked at the weight force. It's just equal to mg. It's really the force of gravity. The normal force is always going to be perpendicular to the surface. Most of the time it's equal to the weight, practically speaking, but it doesn't have to be. Here somebody's pushing down on the book. Whatever force is up has to be equal to all the forces down. So here's the weight force from the earth, this outside force from your hand. Now, if you took the weight plus this force, it would equal to the normal force. We've seen tension when we talked about ropes. Today we've talked about static friction. That's the frictional force before something moves. Okay. We've also talked about kinetic friction. That's after it's already moving, mu sub k times the normal force. And then we looked at the drag force. And I think there's 1 or 2 homework questions on the drag force as well. Interacting objects come into play with Newton's third law. So the third law states every force occurs as one member of an action-reaction pair. We saw this a little bit in the previous chapter when we just first started talking about forces, but we'll see it again in this chapter. So 2 members of an action-reaction pair point in opposite directions, equal in magnitude, but opposite in direction. So to analyze block A's motion, we need to identify all the forces acting on block A. So the person is pushing on A. A is going to accelerate to the right. So what sort of prevents A from accelerating as much as it could? It's in contact with B. So if I looked at the free body diagram of A, I would have to include that force, the normal force between A and B, and it would look something like this. Okay, so for this is just for A, I'd have the normal force, the normal force from the ground. I'd have the weight on A from the earth. I would have the force from the hand this way, force from hand. And then I'd also have the normal from B on A. So the normal from B on A. Okay, so something like that. So here's the force from the hand. Here's the normal force from the ground. Here's the weight. Here's the normal from B onto A. This would be the free body diagram of just A. Now, I could also do the same thing for B. Let's look at the free body diagram on B. I'll just kind of maybe try to do it in place here. Here's the normal force from the ground. Here's the weight from the earth. This is on B. That one up there was from A. And what really gets B moving, if you think about just the forces acting on B, it's the normal force from A on B. That's what actually gets B moving if you just were focusing on B. So the normal force from A on B, this one, and the normal force from B on A, this one here, those are third law pairs. Those are equal and opposite. So third law pairs always come from two separate free body diagrams. So here you have a free body diagram for A, free body diagram for B. This third law pair comes from a pair of free body diagrams. One thing that we also know here, these blocks are moving together, so the acceleration is the same. Okay? So here's an example we can take a look at. So we have a picture here of a 5 kilogram block being pushed with 3 newtons in front of a 10 kilogram block. The two blocks move together. What force does A exert on B? So here I've just drawn a picture. Here's the free body diagram of B. Normal from A on B. Normal from the ground, and the weight. This is for B. So this is, again, just the free body diagram for B. So if I wanted to use Newton's second law for this, I would say that the net force, this is just, again, for B, the net force, mass of B times A, and then what's the actual force acting on B? Well, it's the normal from A on B, which again is equal to the normal from B on A. So if I could figure out the acceleration, I know the mass of B, 10 kilograms, then I know the normal force. Okay, so that's the key here. I've got to figure out the acceleration. Now if I think about this mass A and mass B as a system, I can get the acceleration. So I'm just looking at it as a system now. So whatever we want to call it. This is both of them together. Here's the free body diagram of them together. Normal force, weight. This is the combination of A and B. And then here's the actual force by the 3 Newton force. So this is just, again, looking at them as a system. I could say that the net force is mass AB, I'll call it, times the acceleration. And then what's the actual outside force? Well, from the free body diagram, it's just 3 newtons. So I can get the acceleration then. So mass AB, that's this 15 kilogram system. Okay, so then the acceleration would be 3 newtons divided by 15 kilograms. 2 meters per second squared. So the system's accelerating at 2 meters per second squared. That means block A and block B also have the same acceleration. So then I can come back over here and put in this 2 meters per second squared. Okay, space is getting a little bit tight, but I can do that here. This is 10 kilograms, and now I've solved for A. This is 2 meters per second squared. Oh, actually, sorry. I don't know how I got 2 here. This should be 0.2, right? 3 divided by 15. That should be 0.2. 0.2. And then you get 0.2 times 10. That would give us 2 newtons. That's this whole thing here. Normal from A on B. 2 newtons. And then if I want to, I can come back here. This is 2 newtons. So of the 3 newtons, 2 newtons, you can think about it like this. Of the 3 outside force, 2 of them are being used on mass B. Just for fun, let's look at the free body diagram of A real quick. I'll do it up here. This is 3 newtons. Now we know that this has to be 2 newtons, right? We also have the weight and the normal force. This is the free body diagram of A. So there's 3 newtons, that's the outside force from the person. There's 2 newtons back to the left, that's the normal from B on A. So the net force on A is actually 1 newton, right? 3 newtons to the right, 2 newtons to the left. 1 newton is being used for A. So of the 3 actual newtons of force, 2 of them are being used for B, and 1 of them is being used for A. Okay, that's one way of thinking about it. All right, let's take a look back at the notes. So it's one of these quick check ones for us. Box A and B are being pulled to the right on a frictionless surface. The boxes are speeding up. Okay, that means there must be a net force on them. Box A has a larger mass than B. How do the tensions compare? So T1 and T2. Well, we can get this by looking at the free body diagram of B. So here we have tension 2, normal force. This is again the free body diagram for B. The weight of B, and then we got T1 back this way. Now they tell us it's speeding up, right? There's got to be an acceleration this way because they tell us it's speeding up. So looking at the free body diagram of B, the only way that B is going to speed up is if it has a net force. To have a net force, T2 has got to be bigger than T1 for that to happen. So T2 bigger than T1. For that to accelerate, it has to have a net force. Okay? Good. So by looking at B, we can figure out the answer to this question. Okay, and then we'll do 43 and 46 in class next time. Okay, so the rest of the slides are just a review of the entire chapter. So hopefully you got some use out of this. We'll go over some more example problems, but that really sums up chapter 5. Okay, talk to you soon. Bye-bye.